Hello and welcome to Data Science Corner. This is the first video in the PySpark series. We are going to cover all the topics from beginner to advanced, and all of this will be done hands-on. So first we are going to cover some basic topics which are needed to do the hands-on. Now, Apache Spark. What Apache Spark is? Apache Spark is a comprehensive analytics engine for big data processing. Featured integrated modules for streaming, SQL, machine learning, and graph processing. Spark can be viewed as an advanced version of MapReduce. Now, the difference is, unlike MapReduce, Spark retains intermediate data in RAM rather than on disk. This in-memory data processing enables Spark to process large dataset much faster. Now let's look into the features of Spark. Speed computation. So Spark is capable of running applications up to 100 times faster than Hadoop for large-scale data processing, and up to 10 times faster when running on disk, thanks to its in-memory computation. This speed advantage is due to fewer read-write operations to disk compared to MapReduce. Now, by storing intermediate data in memory and utilizing more RAM, Spark minimizes network and physical storage input-output, making it ideal for real-time or near real-time data processing. Ease of use. So Spark is written in Scala, and Spark provides APIs for Scala, Java, Python, R, and SQL. And it offers the flexibility for developers to build parallel applications in their preferred language. Advanced analytics. In addition to MapReduce operations, Spark supports SQL queries, streaming data, machine learning, and graph processing, and enabling advanced analytics capabilities. Fourth one is multiple data sources. So Spark can read from and write to any storage format compatible with the Hadoop framework, such as HDFS, AWS S3, HBase, Cassandra. It can run on various cluster managers, including its standalone cluster, EC2, Hadoop, Yarn, Mesos, Kubernetes, and integrate with Apache Hive and other data sources. Components of Spark. So let us briefly discuss the different components of Apache Spark. The first one is Spark Core API. So Spark Core is the primary execution engine for the Spark platform, upon which all other functionalities are built. It provides fault tolerance, in-memory computation, resource management, and access to external data sources. Additionally, it offers a distributed execution framework supporting various programming languages like Python, Java, Scala, SQL to facilitate development. Now, let's talk about Spark SQL. So, Spark SQL is a module designed for working with structured data, enabling querying with Spark programs. It supports Java, Python, R, and SQL, and can integrate with diverse data sources including Hive, Avro, Parquet, JSON, and JDBC. Spark SQL can also support HiveQL syntax, allowing access to existing Hive warehouses. Spark streaming. Now, Spark streaming utilizes the Spark Core API to conduct real-time interactive data analytics, benefiting from Spark's inherent fault tolerance. It can integrate with a wide range of popular data sources such as HDFS, Flume, Kafka, and Twitter. Spark MLlib. So Spark MLlib is a scalable machine learning library built on the Spark Core API, delivering high quality algorithms. It can be used with any Hadoop compatible data such as HDFS, HBase, or local storage, making integration into Hadoop workflows straightforward. MLlib is available for use in Java, Scala, and Python as part of Spark applications. GraphX. So GraphX is Spark's API for building and executing graph parallel computations. It allows user to interactively build and transform graph structured data at scale. So these are the components of Spark. Now let us look into Spark architecture. Spark employs a master work architecture similar to the Hadoop framework, where the master node is the driver and the worker nodes are the slaves. This cluster system comprises one master and multiple worker nodes. On the master node of a cluster, the driver program schedules job execution and manages resources using the cluster manager. When a Spark is initialized or a Spark submitted executed on a cluster, the Spark context is created by the driver program on the master node. Spark context is the primary entry point for Spark functionality. How Spark works is first data partitioning. The Spark driver program divides large input of data into smaller chunks, typically sized at 64 MB, 128 MB, or 256 MB, and distributes these partitions across multiple worker nodes for processing. And task distribution. Spark context splits a job into multiple tasks, which are then distributed to worker nodes. Each task is executed by the individual worker nodes or slave nodes and managed by the driver program through Spark context on the master node. Next is task execution and reporting. So worker node executes the assigned task and report the status of each task back to the driver. The number of concurrent tasks is equal to the number of partitions. In resource management, so Spark context collaborates with the cluster manager to handle various jobs. The cluster manager allocates resources such as CPU and memory to the worker nodes where tasks are executed. Spark supports several cluster managers, including standalone cluster manager, Hadoop Yarn, Kubernetes for resource allocation. So let's talk about Spark internal workflow. First, when a Spark application code is submitted, the driver program on the master node initializes Spark context. This process implicitly converts the Spark code, which contains transformations and actions, into a directed acyclic graph, or we can call it DEG. A DEG represents a sequence of computations on the data. Then the driver program performs optimizations and translates the DEG into a physical execution plan comprising multiple tasks. It decides which tasks will be executed on each worker node and schedules the work accordingly. After allocating the tasks, the driver program negotiates with the cluster manager to secure resources for the worker nodes. The cluster manager then launches executors on the worker nodes on behalf of the driver. Before starting execution, the executor registers themselves with the driver program, allowing the driver to maintain a comprehensive view of all executors. Executors report the status of each task back to the driver. Now let us talk about PySpark API. So PySpark API is the Python API designed to support Apache Spark. Python is one of the most widely used programming languages, particularly in data science, and is easier to learn compared to many other languages. Many data practitioners are already familiar with Python's pandas library for data transformations and manipulations for extract insights. Developed with strong support from the open source community, PySpark utilizes the Py4j library. Now, why it is advantageous to use PySpark? So Python is very easy to learn and implement, offering a simple and comprehensive API. So PySpark provides an interactive cell for analyzing data in a distributed environment. PySpark also supports various options for data visualization, which is more challenging to achieve with using Scala or Java. This is all for this video. I know this video is completely theoretical. However, from the next video onwards, we'll be doing all the topics, all the concepts hands-on only. So we'll see you guys in the next video. Thank you.